By the laws of our best physics, the universe should have erased itself in its first second. Our best early universe models predict near total annihilation. And yet, here we are. The standard story feels stable. The Big Bang happens. Energy floods space. Particles form. Stars ignite. Galaxies assemble. Life eventually appears, clean, sequential, logical. But buried inside that story is a contradiction so severe that under standard cosmological models, almost no matter should be here at all. Not stars, not atoms, not you. Modern particle physics rests on an idea called symmetry. In the 20th century, physicists discovered that nature treats matter and antimatter almost identically. For every particle, an electron, a proton, a quark, there exists an antiparticle. Same mass, opposite charge. When matter and antimatter meet, they annihilate, not metaphorically, literally convert into pure energy. According to the Standard Model and early universe thermodynamics, matter and antimatter should have been produced in nearly equal amounts. Equal, which means that within fractions of a second, matter and antimatter would have annihilated almost completely into radiation. The result? A universe filled with light, and nothing else. No atoms, no chemistry, no structure. But that is not the universe we observe. We see stars, galaxies, black holes, planets. Something tipped the balance. And the imbalance is extraordinarily small. For roughly every 10 billion matter-antimatter pairs in the early universe, only about 6 extra matter particles survived. That tiny excess, roughly a few parts in 10 billion, is why anything exists. If the numbers had been perfectly equal, the universe would be empty radiation. Instead, the tiny surplus became everything. The question is simple. Where did that extra one come from? The mystery has a name, baryogenesis. Baryo for baryons, particles like protons and neutrons. Genesis for origin, the origin of matter itself. In the 1960s, physicist Andrei Sakharov outlined 3 conditions required to produce a matter-dominated universe. First, baryon number violation. Second, C and CP symmetry violation. Third, departure from thermal equilibrium. That sounds technical. It isn't mystical. Think of it like baking. If you want more of one ingredient than another, you need a rule that allows imbalance, a bias in the mixing process, a moment where the system freezes before balance restores. In early cosmic time, the universe was unimaginably hot. Particles collided constantly. Reactions happened forward and backward equally. In equilibrium, symmetry dominates. To create matter excess, something had to push the system slightly out of balance, just long enough for the bias to stick. We have observed small violations of CP symmetry in certain particle decays, particularly in experiments involving kaons and B mesons. These were detected at facilities like CERN and SLAC. But here's the problem. The amount of CP violation we measure is nowhere near enough to explain the cosmic imbalance. Not even close. Yet the universe we observe is clearly matter-dominated. Within the Standard Model framework, the predicted CP violation is several orders of magnitude too small to account for the observed baryon asymmetry. Something is missing. Now we escalate. Look at the cosmic microwave background, the afterglow of the Big Bang, precisely mapped by missions like Planck. It tells us the ratio of baryons, ordinary matter, to photons. That ratio is approximately 6 parts in 10 billion. Write that down, 6 in 10 billion. That is the surviving asymmetry, which means that for roughly every 10 billion matter-antimatter pairs, only about 6 extra matter particles survived annihilation. Everything else vanished. Stop. Think about what this implies. The entire observable universe, every galaxy, every atom in your body, exists because of a tiny asymmetry on the order of 1 part in a billion. That is not a rounding error. That asymmetry is the reason any structure exists at all. Now, here's the deeper tension. The standard model of particle physics, one of the most experimentally confirmed theories in science, does not generate that imbalance naturally. It requires new physics. Possibilities include leptogenesis, asymmetry, emerging first in leptons, then transferred to baryons, electroweak baryogenesis, asymmetry forming during a phase transition, grand unified theories introducing heavy particles that decay asymmetrically. Each scenario demands conditions or particles we have not yet confirmed. The Large Hadron Collider has searched. So far, no decisive evidence. We are staring at a measured fact, and our best theory cannot explain it. Now the tension deepens. There is another layer to this instability. Measurements of the Higgs boson mass, discovered at CERN in 2012, suggest something unsettling. When combined with the top quark mass, calculations indicate that our universe may exist in a metastable vacuum, not the lowest energy state possible. Stable for now, but not absolutely stable. Imagine a ball resting in a shallow valley, not the deepest one available. Given enough time or the right fluctuation, it could tunnel into a deeper state. If that happened, the vacuum state of our universe would shift, altering particle masses and interaction strengths. Atomic structure as we know it would no longer be stable. Chemistry would not function in its current form, all at the speed of light. This conclusion follows from renormalization group calculations in quantum field theory, using the measured Higgs and top quark masses. Now connect the dots. The universe barely avoided self-annihilation at birth due to a tiny asymmetry, and it may not even occupy the deepest possible vacuum state today. Stop. Think about what this implies. Existence is balanced between two instabilities. Too much symmetry, nothing exists. Too little stability, nothing persists. And we are inside that narrow window. So what are the options? Option 1. There is new physics beyond the standard model that explains baryogenesis cleanly. We simply haven't detected it yet. Heavy sterile neutrinos, supersymmetric partners, unknown CP violating processes. Option 2. The asymmetry is environmental. In a multiverse scenario, different regions of reality might realize different physical constants or symmetry breakings. Most regions annihilate into radiation. A few, extremely rare, achieve a slight imbalance. Observers can only arise in those rare pockets. In that case, the universe does not need to be typical. It only needs to be compatible with existence. Neither option is comfortable. One demands undiscovered physics. The other demands a redefinition of what fundamental even means. Either way, the conclusion is unavoidable. A perfectly symmetric universe would contain almost no structure. Ours unmistakably does. It is a consequence of broken symmetry. And broken symmetry is not the default. It requires explanation. Here is the quiet reality. Every atom in your body exists because in the first second after the Big Bang, nature failed to perfectly balance its own equations. A slight violation, a microscopic preference, a frozen accident. If symmetry had held completely, this would be a universe of radiation and silence. Instead, it is a universe of structure, and we still do not know why. The deepest laws we have describe how reality behaves, but not why it survived. The fact that ours does is one of the strongest clues that our current theory is incomplete.